Um, Welcome to the Winds and Currents webinar today. Jinbo Wang from JPL is going to talk about near-inertial oscillations and their relations to the proposed Odyssey mission. So opportunities and challenges. And thank you, Jinbo, for being willing to do this today.
Okay, thank you, Sarah. Should I start?
Yeah, go ahead.
Thank you. Yeah, thank you, Sarah, and thanks everybody for dialing in. So as Sarah mentioned, today's topic is near inertial oscillations to Odyssey, opportunities and challenges. So I hope this is a good opportunity to seed some discussion as requested by Sarah. This is more like a discussion than just presenting some results. This is ongoing work. A lot of things we find and a lot of things we plan to do. Basically, this presentation is a collection of a community's work with all the names listed here. There are a lot of people at JPL that we have collaborating on. Hong Zhang, Hector, Alex, Dimitri, Patrice, Ernesto all contribute to this work. And we also have a lot of input from the community, including Lee, Clement, Brian, Shane, Eric, Matthew, Fabrice, and Orlean, Sarah, and Luke. All right, so this is the outline of today's talk. First, I will briefly introduce what the Odyssey observations will look like and introduce the challenges from the near inertial oscillation. And second, I'll talk about the data, tools, and methodologies I'm going to use in this work. And then third one, we show the results. I want to emphasize the two categories in the result. One is the weak eddy region, and another is energetic eddy region. So we want to present the challenge of NIO in these two scenarios. And finally, I would like to bring some discussion topic that we can build on and to understand the challenges and opportunities of NIO for Odyssey. This is an example of the Odyssey observations. It is 5 kilometer grids with 30 centimeter per second noise on the 5 kilometer grid. It has a wide swath between 1600 to 1800 kilometer wide, approximately twice a day measurements at mid-latitude. So the high frequency coverage is because of the wide swath. You can see that from this swath, even though there is a time difference, you can see from the image, the 2D image, the velocity of the currents, Kurshu and Gulf Stream is very clear. Now, because of the twice a day mid-latitude temporal sampling, immediately we'll think, how will this temporal sampling recover the near inertial oscillation, which is very energetic in this in velocity field, not in altimetry, but velocity has a lot of inertial oscillation and it's a very clear high frequency signal. This is an example of the aliasing effect. I want you to focus on the green line and the red line. The red line is the inertial period. This is horizontal is the latitude, and vertical is the log scale of the period in days. So the green line is the designed orbit now. Previously, there is another orbit that we consider is cheaper, but now we pretty much fix it to the wider swath. That's the green line sampling period, and the red line is the inertial period. So to fully resolve the inertial period, we expect the green line is half, at least half, and smaller than half of the red line. But it is not, especially in the mid-latitude. The green dashed line is the earliest period. So because of the aliasing that the temporal sampling cannot resolve the inertial period, we will be thinking about how much of the aliasing can happen in the mean latitude between the 20 and 60 north. We will have observations from moorings, surface current, that each dot here is the mooring we tested. Especially, we will focus on the Crucial Extension Observatory and the Station Papa between 30 and 50 north. So the next data, tools and methodologies. This is the 5 moorings we used to study this problem. There are 5 moorings, but we focus on the Crucial Extension and the Station Papa for its representative of 2 dynamic regime. One is the low kinetic energy in the low eddy kinetic energy in Station Papa, and energetic Crucial Extension. The initial period is about 22 hours for Crucial and 16 hours for Station Papa. And the analyzed period is 1 year between 2007 and 2008. There are more data than just this 1 year period, but as an illustration, we just show this 1 year analysis. First of all, what is the ratio of the near inertial oscillation relative to total kinetic energy? So this is the result from the 5 moorings. So we basically do a bandpass filter to get the near inertial oscillation signal and calculate the mean speed, and then also calculate the low frequency, which is a sub-inertial frequency, and calculate the standard deviation of the current speed. So the horizontal axis is the low frequency, the vertical axis is the near inertial oscillation component. You can see that because of the different scale, the 1-to-1 ratio is this line. From this figure, you can see that Station Papa has more inertial oscillation energy than the sub-inertial oscillation, sub-inertial frequency. But all other 5 stations has dramatically more eddy energy than inertial oscillation, especially the crucial extension region that is more than order of magnitude higher than the inertial oscillation. So there is a number next to the name of the each mooring station. That means the percentage, not percentage, the ratio between near inertial oscillation to the total high frequency energy. 0.8 means 80% of the high frequency variability is due to near inertial oscillation. The higher the number, that means if you look at the time series, then pretty much you will see is just the near inertial oscillation. But if the number is low, that means near inertial oscillation is only a tiny bit of the total high frequency variability. So Station Papa has 80%, and Crucial Extension region, it has 50%. This small near inertial oscillation relevant to total is also confirmed by Luke's result based on the high frequency radar of the California coast. So this is the region Luke analyzed, and on the left, this curve is the fraction of the spectral power at near inertial band relative to total. And you can see that the maximum here is happening here around 44 north. It's about 15%, but mostly just 5 to 10% of the total energy is in the near inertial band. So that gives us first a clue that probably the aliasing, even there is aliasing, it should be fine. It's definitely less severe than the case that barotropic ties to altimetry. The barotropic signal is much more stronger, stronger than the baroclinic signal in the altimetry. So this is one of the methods we used to tackle this problem. If we have less frequently sampled signal that cannot cover the near inertial oscillation, we can inject some simple dynamics to recover it. This is a simple idea that we have been using. This is some existing. This work is we've done this before the selection of the name, so you can still see the Wacom name all over. Basically, we use a simple slab model without background shear and vorticity, and also with ties. Try to fit this model to the Odysea observations. The slab model is also driven by observed wind stress. That's another observable from this mission. We also use hourly data from fine moorings to set the benchmark. So the slab model is well known, it's very simple. So given an initial velocity, u0, and mixture depth, and the time series of wind stress, we can integrate this slab model and then regenerate the response. This model can also be solved analytically, but if we have a time varying wind stress, so integrate numerically is much easier. We also include ties by simple tidal harmonics, and then end of the day we minimize this cost function. Basically, is the prediction of the slab model and prediction of ties, and minus observations and bias. The control parameters is initial velocity, mixture depth, and decay parameter, and this is the bias coefficients, bias and the tidal coefficients. Okay, I'll skip this slide. Another method we use, this is a basic Clemens result. This Clemens previous work for scheme, and use a convoluted harmonics of near inertial frequency to fit a localized harmonic model. Obviously, this is only part of the solution in Clemens method. Clemens also use spatial information as well as the assumption of the geostrophic velocity from altimetry. But here, Clemens helped us to did a simple test on the time series mooring velocity that plug in these convoluted harmonic analysis into the time series of the mooring. Finally, we also tested another idea that can we use realistic wind forcing force a medium resolution model, just make a forward run. Can this model predict the ocean response to the real wind? So this is Hong Zhang's work. We use 160-degree MRT-GCM forward simulation forced by ERA5 hourly wind, including barotropic tides. The simulation is done between 2004 and 2009. And this is spin up from the rest. You can see from a spin up from the 1992. By the time of 2004, it's already getting equilibrium. By comparing to lower resolution MRT-GCM, you can see that increase the resolution, the total mean kinetic energy is increased. The purple one is the 160-degree forced by ERA5. and because it's hourly wind, it has more energy than other simulations with 6 hourly wind forcing. This is the example of the surface zonal velocity from this simulation. Okay, so now next I'm gonna go to the results. Again, going back to this review where we are for this is station Papa, where the near inertial oscillation is stronger than the sub-inertial frequency. So this is an example of the time series. You can see that the observation is orange line. The orange line, you can see very clear in near inertial oscillation in this total velocity, both zonal and meridional. Basically, this is illustration of what we see here, this quantification. Now, because, as you can imagine, because the signal is so strong and so clear, it is rather easy. For this case, we can reconstruct regardless of the methodology that we'll show later. This is an example of the aliasing effect. Because the signal is so clean for the near inertial frequency band, if we just sample using the averaged time period from the Odysea sampling, and then calculate the frequency spectrum from the mooring truth and also from the synthetic satellite observation, this is the result. Again, focus on the blue and orange. The blue is the hourly observations from the mooring. This is clockwise, and this is counterclockwise, the rotary spectrum. There is a very strong signal, very strong peak at inertial frequency here from the blue, and from orange you can see that these frequencies inertial oscillation is captured, but significantly reduced to order magnitude smaller, which is expected because we do not have high frequency sampling. But at low frequency, the aliasing is not severe for clockwise, but the clockwise aliasing actually went to counterclockwise component that you can see from here. There is orange peak here and here. Basically, it's around, excuse me, around 4 days aliasing. But if we think about the even lower frequency that with a period longer than 10 days, the Odysea sampling actually is fine compared to the total. That means the aliasing is not as dramatic as we thought, and the aliasing effect actually went only to the period between 1 and 10 days. Okay, this is the scenario that we don't do anything. Now, if we plug in the slant model, because we have the dynamics constraint in with the model or with the data, we actually can do a better job. There are 4 panels. Let's focus on the right-hand side, 2 panels. The top is the simplified Odysea observation. In blue, the blue dot is almost a twice a day measurement from the observations. And the truth is the gray line. I'm not sure whether you can see it clearly. And predicted based on the Odysea observations is the red. And the green is a filtered near inertial oscillation truth. Because the station Papa high frequency variability is dominated by the near inertial oscillation, you can see the green and the gray curve pretty much the same. This is another confirmation that the near inertial oscillation is dominating in this station. And if you compare the red curve and the green curve, they are matching each other pretty well. The SLAM model prediction can explain more than 95% of the variance, and with the exact phase. Now, this is a recovery of the near inertial oscillation based on the synthetic Odysea observations without noise. If we add 10 centimeter per second random noise into the observations, which is this panel, you can see that the blue dots is deviating from the gray line. That because of the noise. But even with that noise, the prediction is the red line still match the green line pretty well. So that means the signal is so strong that it's not sensitive to the measurement noise or infrequent sampling. So this is another quantification based on the previous results SLAM model. The top panel is the excuse me, velocity with 5-day mean, boxcar mean. The truth is the blue, and the SLAM model prediction is the orange. You can see they match pretty well. And also we calculate the NIO wind work because we have wind stress observations at the same time. Also, the error is less than 20%. The truth is from is showing in blue, and the SLAM model is orange. Now, this is the harmonic analysis by Clement, plugging his methodology of the synthetic Odysea observation from station Papa observations. The ground truth is the black curve, and observation is the black dot from Odyssey. And the basic mapping basically did not consider the near inertial oscillation, which is the blue curve. This blue curve should be expected from the existing data product such as Oscar. And the red one is the reconstruction considering the near inertial frequency oscillation. And you can see that this method also predict pretty well. Now, the crazy thing is this one. As I mentioned, we run a forward simulation with the 1/6 degree MIT GCM without any data simulation. What is real here, it basically is the ERA5 already wind and nothing else. And the observations here is shown in orange. The zonal velocity is on the top panel, and the meridional velocity is on the bottom panel. The model is blue. You can see that when the inertial oscillation is stronger, actually the model can predict the observed from the mooring, both in amplitude and phase. It's like the SLAM model least square fitting or harmonic analysis. This is completely independent. The model does not see the observations. It just feels the wind. That brings us to the conclusion that in this area with less mean flow and eddies, basically the signal of the wind-driven near inertial oscillation is so strong, so that even this forward simulation can predict the near inertial oscillation very well. This is an example of the forward MIT GCM simulation in a rotary spectrum. The top panel is counterclockwise, and the bottom panel is clockwise. And the blue line here is the model, and observation, mooring observation is from the orange line. You can see the model underestimate the super high frequency, but with a low frequency and also inertial frequency, the model actually did a pretty good job in terms of the energy level compared to the observations. Of course, the model does not reproduce the mean flow, even though it's weak. The mean flow does not agree between models and observation, which is understandable. But at near inertial frequency, the model and the observations actually agree more than 90%. So this is just a summary to have two methods in this one diagram with a crazy level of random noise. What happened? Sorry. So the truth is the a gray line here. The simple harmonic analysis. This is different from Clement's method. Here, what I use is just a simple harmonic without any kernel modulation. The red line is the SLAM model. The green dots are the Odysea observations. The top panel is less frequent, like twice a day measurement. The bottom panel is, hypothesized hourly observations from the satellite. You can see that the SLAM model and harmonic analysis in both cases agree pretty well. That means in this case, less frequent sampling does not matter. Increase the frequency of the sampling does not increase dramatically for predicting scale. So the conclusion is that in regions with low frequency, with a low EKE and energetic NIO, the NIO signal is easy to distinguish and reconstruct from the Odysea observations. Now let's move to this region. As you can imagine, we will have trouble to reproduce the good result from the station problem. Now let's go directly to the result of the SLAM model reconstruction. Let's focus on the right panel, which is the fixed orbit right now. If we compare the observations, which is the black curve, and SLAM model is the blue curve, you can see the fit also pretty well in this case. By the way, this is already high pass filtered with a signal only with the period shorter than 5 days. So you don't see the energetic mesoscale signal, and it's around 0 here. The Wacom observation is the orange line, orange dot harmonic component is the green. But if we add 10 centimeter per second random noise, which is this panel, the reconstruction start to degrade, but we can still see the cracked phase and cracked amplitude. In this case, blue line, the SLAM model prediction against the observations is the solid black. Now, this is a good case that after a strong wind event in this region, we see clear near-inertial oscillation signal. Now, another case is not so good case is this one that during this period, there are high frequency variabilities. You can see from the gray dashed, and the green line is the synthetic Odysea observations. But this high frequency variability is dominated by tides and small mesoscale eddies, not particularly near inertial oscillation. For this case, together with some random error from the synthetic random error, we cannot reconstruct the near inertial oscillation So in this case, the signal is not so clear in the observations, regardless whether you have noise or no noise, the SLAM model cannot distinguish the NIO from other high frequency variabilities. So if we do a statistics or 1 year period, let's see how I'm doing with time. This is the 2-error statistics. So on the left, we plug in the SLAM model to hourly monitoring observations, which is setting a benchmark for our SLAM model methodology. If we use hourly observations to fit that SLAM model, we can get statistically about 3 centimeter per second error between SLAM model prediction and hourly monitoring observations. Now, if we subsample the observations using 12-hourly scenario, the SLAM model prediction error went up to more than 10 centimeter per second in the crucial extension region. In this region, if you remember what I presented for the station Papa, the hourly and the 12-hourly SLAM model prediction does not differ much in that scenario. But for the crucial extension region, the sampling actually degrade the SLAM model prediction scale. Again, because the other high frequency variabilities. As you can imagine, that if we just use the forward MITG SAM, not only the eddies are not in the right place, the near inertial oscillation also becomes less coherent, less correlated between model and observations. Now, this is a global statistics. Previously, we analyzed based on the single time series of each monitoring. We use the forward simulation hourly output and plug in the SLAM model. And this is a fitting error. This is understandable that over the storm track region in the mid latitude, for example, in this region, we have higher fitting error. But even in higher fitting error region, the error only amount to 3 centimeter per second because we have high frequency observations here. The SLAM model fitting is to the hourly model output. That means the SLAM model has scale, and the model physics, if we resolve in a high frequency, the SLAM model can represent the model physics to a high degree. That this is at least from a modeling perspective, is confirmation of the relevance of this SLAM model, even though it's simple. So now this is a conclusion with our existing results. So again, in regions with low EKE and a high NIO is very easy to reconstruct regardless of methodology, and it's a low threat to Odyssey. So in regions with a high EKE and other super inertial motions, NIO can be a challenge to reconstruct from methods that are based on the single time series analysis that we presented so far. Now, what to do? We have a hypothesis. The eddy wave interaction introduces dynamics that the SLAM model does not include, which is, to the community should be trivial based on so many nice papers about this eddy wave interaction. The second hypothesis is use the wide swath two-dimensional measurements and the eddy wave interaction terms. If we plug in the eddy wave interaction term back into the SLAM model, also consider explicitly eddy dynamics in the least square problem, we should be able to increase the accuracy of the NIO reconstruction. So later I will stress the importance of the two-dimensional wide swath, the benefit of it. This is a great opportunity, in my view, that we can use these two-dimensional measurements to not only just avoid NIO contamination or aliasing, but actually to study the wave-eddy interaction. A simple problem can be just to do a data assimilation. So this is the future work. We will use the new coupled ocean atmosphere simulation to conduct a global analysis by fitting the SLAM model and the additional simplified eddy model to the wide swath Odysea measurements. I will introduce the coupled simulation later. The second one is quantify the spatial scales of a near inertial oscillation using drifters. This is a work with Olian and Shen and others. Just briefly, you may have heard that follow the LSE 4320, Dimitri and colleagues have been doing this coupled high resolution coupled ocean atmosphere simulation. And this will be a perfect playground for us to do OSCE. A couple of us at JPL have been analyzing it, but it is really open to the community. Thanks to Dimitris and the team. If you are interested in it, let us know. We can help pass along the data. So this is coupled simulation that coupled MRT GCM and JOS5. The horizontal resolution is about 7 kilometers in mid-latitude, and it's hourly outputs. We have 14 months of model output now. The total data ocean plus atmosphere is about 3 petabyte. But if we only focus on the surface layers, it should be manageable. This is a preliminary validation or evaluation of the model surface velocity field against the drifter measurement. So this is a work by Shen and Brian. So on the left top panel is the drifter near inertial oscillation variance. In the middle is the coupled MRT-GCM. And on the right is the equivalent MRT-GCM at this resolution, but just the force, which is the LSE 2160, 1/24 degree simulation. You can see that by coupling to the atmosphere with high frequency coupling process, the near inertial oscillation is significantly stronger than forced simulation. The forced simulation is by 6 hourly wind. If we do the zonal average on the bottom panel, we can see more clearly. The forced MRT-GCM is the green curve, and the coupled MRT-GCM is the blue curve, and the drifter result is the red. The coupled simulation is still weaker than the drifter observation, with some caveats of different different analysis method. One is Lagrangian, another is Eulerian. But even with that uncertainty, we see that the coupled simulation still underestimates the truth, but significantly improved against the forced counterparts. Okay, now I just want to throw out some discussion points. The first one, I want to illustrate the benefit of wide swath, and then thinking about the natural filtering by spatial differencing, because we have direct velocity measurement on a wide swath. That's a two-dimensional velocity field. We can do a lot of fancy stuff that we cannot do from altimetry. We can do we can calculate shear, strain, vorticity. Will those a quantity be a problem for NIO, or will NIO be a problem for those quantities? The third one is I will show an example of what we are missing now, but it can be fulfilled by Odyssey. So here is a simple illustration of 1D versus 2D measurement, needle versus wide swath. On the right-hand side of this panel, I showed a signal of 50 centimeter per second signal amplitude and 50 centimeter per second random noise. By looking at this curve, I'm not sure whether you can see anything. Maybe you can guess, but definitely it's not with a high degree of certainty. So if I mask this 2D field, well, from the 2D view, I guess it's easier to identify the signal than noise than the 1D view, even though the noise is the same noise, then signal is same signal. What happens here is that we can naturally pick up the 2D information with the spatial structures. 2D give us phase. So that makes that makes it easier job for us to single out the signal from the noise field. This is the true signal on top of the noise, but I can imagine that it's hard to diagnose this from the noisy field from the one-dimensional measurement. Now this is another animation I want to illustrate 2D versus 1D again. Let me play this animation. It's a long animation, 6 minutes, but I'm gonna show the original speed and then speed up later. What we see here is the zonal velocity on top left, meridional velocity on top right, and the zonal meridional 2D wave number spectrum of these two velocity field. Now I just play. I want you to watch and see whether you can identify anything that from this satellite observations from Odyssey. Wide swath again. You can see that there are crucial extension meanders. Also, there are inertial oscillations, large scale patterns by the atmosphere forcing, and internal waves. The internal waves is relatively weak than the eddies in this region, but you can still see it. From the wave number spectrum, you can see the interesting structures actually can give you time evolution. You can imagine you can do flux analysis from this field. Now I'm going to speed up. As I talked with Sarah earlier, if I speed up the animation, it's like a natural low pass filter. You will pick up the low frequency, high frequency will pass quickly. This is 10 times faster. Even with the 10 times faster play speed, you see the crucial extension meanders and eddies very quickly. The higher frequency already passed and cannot be identified, which is also the effect of a low pass filter. And there are a lot of interesting things happening in the wave number spectrum that we cannot comprehend right now. But the point is, there are signals in it, and it's twice a day. We can plug in some advanced machine learning methodology. For example, recently developed the Fourier neural operator exactly can fit into these observations for prediction and gap fading tasks. All right, so natural filter. So if we have a wide swath, we can just do a spatial differencing. But here is not a Oscillations, it's just a model illustration. On the left is the kinetic energy with number frequency spectrum, which is well known and well understood. And this particular frequency, in inertial oscillation, we have large scale inertial oscillation signal here in the velocity itself. But if we take the relative vorticity, and most of the high frequency and wave signal is gone. What's left is the balanced motion actually extend all the way across the inertial frequency. There are some leftovers with the waves and at near inertial frequency band. Remember, this is a relative vorticity, not potential vorticity. So with wide swath, we can do spatial derivatives and analyze the quantities that actually is important in the energy budget for near inertial oscillation and other processes. So the last one is on the question that what are we missing now? What can Odyssey achieve? In this plot here on the bottom is the zonal velocity from crochet extension region in blue. That's the model hourly observation with the 1 year period. And Odysea, synthetic Odysea observation is the orange. You cannot see the, because this is 1 year long, you cannot see the 12 hourly, but this is 12 hourly observation. The green is the Oscar product interpolated on the crochet extension observatory mooring location. Worth to see that the Odysea observation has already built in a realistic error in it. And you can see, compare the green versus orange, we have a long way to go in terms of observing the true velocity actually can be achieved by Odysea. And particularly, there are 3 events that Oscar product completely missed is associated with the strong crochet extension meander. If we look at the Weir's SST, you can see the eddy is pretty clear there. It's a true signal. This is around 2008 January. This is a temperature anomaly based on the Weir's SST, and this is the station. You can see that these meander start to reach that station during this period, and Oscar missed it completely. And then in the middle of the event, that this meander, a strong filament that actually right past the station. And you see that this basically Oscar product missed the 1 centimeter per second signal eddy here. At the end, these meanders start to retreat, and this is the end of this 1 month period. If you use this product and the temperature field to do, for example, eddy flux analysis, V prime, T prime, this will give you a huge error. And this is what Odysea can help us. With that, I'll give you back, Sarah. Thanks.
Well, thank you, Jinbo, for this great overview. This was really wonderful. Questions for Jinbo? There's some questions in the chat.
Okay, I'll quit my screen.
So Clément asks, when you say Oscar missed, you actually mean altimetry missed the signal. Is that right?
I think that's right. Yeah, Oscar pretty much dominated by the altimetry, and Yeah, the Ackermann component is
These are like quasi or pleistrophic edits, I guess. But yeah, okay.
right.
And Megan has some really useful comments about the use of the mooring data. Megan, do you want to speak to that?
Hi all. I just want to say it's really great to see the Keo and Papa data being used. Keo was just redeployed after a long COVID-induced break last month, and Papa's being turned around this week. But please, if you use the data and write papers, let us know so that we can include your papers in the publication list. I put that there in the chat. It's, you know, we always have to justify redeploying and maintaining these long time series, and having these papers really does help with that. And having a, you know, a location where you can go and say there were 70 papers using these moorings in the last 5 years. So thanks.
Yeah, thanks, Megan.
So,
That's great news.
other questions? I have tons of questions if other people don't. But, Shen has raised his hand, so why don't we let Shen go ahead?
Hi, Jinbo, can you hear me?
Yeah, I can hear you, Shen.
Hey, thank you very much for this overview. So as you pointed out, and we see that by analyzing observations, it's very important to take into account the relative vorticity to capture the right, frequency of the inertial oscillations and to be able to apply a correct bandpass, right? So if you apply bandpass, you need to know what the vorticity is. So do you imagine that how are we going to do that with Odysea? Like, are we going to try to combine that with altimetry to get the vorticity at the same time to get a better extraction or prediction of what the NIO are going to be? Or are we going to use SWOT? What do you think we can do?
So, yeah, if we think about the Odyssey observation is in the mid-latitude is twice a day, we can first do a low-pass filter and get the major part of the mesoscale field reconstructed by simple low-pass filter of the two signal. I tested if we apply a 10-day window, a threshold, and with period longer than 10 days, the Odyssey observation itself can give us pretty good recovery of the truth. I would assume that is the major component, and we can use that component directly calculate the vorticity field, a background vorticity field, and then iterate again, coupled with the high frequency component.
All right, thank you.
Yeah.
Can I ask Jinbo, in the Kurshio where things were challenging, you showed that there was sort of a leftover tidal signal. Do you think there's prospect for a better tide model, or something that would make it easier to extract that signal, to differentiate the near inertial from the tidal and other stuff?
Yeah, so that's a good question, Sarah. That brings again the benefit of two-dimensional measurements. We can do a lot of fancy methodology with the 2D field. With altimetry, we have been using Zhongxiang, and Ad and others have been taking advantage of the spatial information together with a narrowband signal to recover the spatial structures. But with the wide swath itself, we can take advantage of those high density observations, even though lower in temporal. I hope that Clement can cover a little bit next week, because his method has taken into account the two-dimensional field. And on top of the altimetry, because we are seeing the same signal from different angles, right? One is velocity, another is height. We can combine these two variables and do a better job in both coherent and incoherent tidal, baroclinic tidal signal.
Thanks. Ernesto.
Hi, thanks so much, Jinbo, for the very great overview. One of the things that strikes me from the results that the spectral results, spacetime's forcing, is that a lot of the energy seems to come from very large scale, very high or fast fronts coming through. And so if you had a mixture between better barotropic modeling of the atmospheric forcing and better observations of the winds from Odyssey, do you think that we could reduce the mitigation of the near inertial forcing to something like is being done in the altimetry for the barotropic forcing that happens using high frequency models? Is that something to pursue?
Yeah, that's a very good point, Ernesto. I think so. I think we should pursue in that direction. And exactly how, I think we should discuss. And this, I think this is a platform, we discuss among ourselves already. This is a platform that invites the community's contribution and involvement in this direction. Yeah, and so my answer is yes, definitely we should go that direction.
This sounds great. We are almost at the end of the hour, and we have the opportunity next week when Clément Ubelman is speaking to continue the discussion about near inertial oscillations. So I hope everybody will be back with lots more thoughts on the topic next week, and we can continue the discussion. This was great, Jinbo. Thank you very much. Big round of applause.
Thank you, Sarah. Thanks, everyone. Okay, I don't see any